Okay, so starting tomorrow, I will also be live streaming in addition to posting what we did on Google Classroom. So both things will be happening. So if you end up that you have to stay home, but you're well enough, okay, you can watch the live stream and ask your questions there, okay? Because I cannot guarantee that if you're watching the podcast later, like, at 8:30 at night, and you email me a question that I'll answer. Okay, so if you can, the live stream would be best if you are in that situation. Hopefully we're all here, but realistically that's probably not going to be the case going forward. Okay, so if you have to stay home, the live stream option will be available to you for my class. I can't promise that everybody else is doing it because everybody has been given freedom to handle this the way they feel comfortable with, okay, and with whatever works best for them. So don't count on the fact that, I can stay home because all my teachers are going to be doing this. Not everybody is, okay, because not everybody wants to do it that way, and that's fine. Okay, there's no right or wrong way to do this. We were actually told, do this, do your best, and know that it's going to be messy. Those were like Mrs. O's actual words to us. Okay, so know we're doing our best, and it's going to be messy. Yeah. All right, so lesson 9 here on properties of waves. So this is the second half of the unit. Okay, the first half of the unit was simple harmonic motion. Now we're going to talk about waves. The reason we do waves second is because waves are caused by something oscillating with simple harmonic motion. Okay, so all of the same types of values are going to apply here. Amplitude, period, frequency, okay, all of that kind of stuff is all still going to be applicable to waves because a wave has to be generated by something that is oscillating with simple harmonic motion, so they will have all the same properties. Okay, so we're going to learn the characteristics of the two types of waves, transverse waves and longitudinal waves. That is spelled correctly. Okay, longitudinal is a type of wave. Longitudinal are lines on a map. They are different things. Okay, all right. Understand how waves are created and how they are propagated, okay, and understand the properties of waves. Like, again, I said they're going to be like period, frequency, amplitude. One new thing will be wavelength, but that's pretty obvious. It would be exactly what the name would imply, the length of a wave. Okay, so that's kind of a no-brainer. Okay, all right. So, a wave is a traveling disturbance. A wave is able to carry energy. A wave is not matter. Okay? A wave travels through matter. The wave itself is not matter. The wave is energy. Okay? Everybody follow me there? It's a little bit weird, okay? Because when we picture waves, we picture the ocean going up and down or something like that, okay? And we picture the water. But the water is not the wave. The water is what we call the medium. Okay? In order for a wave to travel, there has to be a medium for it to travel in. The exception being light. Okay? The reason light is an exception is because light is both a wave and a particle. So it creates its own medium. Weird. We're not getting into that. Wave-particle duality is part of physics 30. Okay? But all waves, with the exception of light, require a medium in which to travel because they have to have something to propagate them. Okay? Something that can oscillate up and down, something that the disturbance can travel through. Okay? That's why there's a saying, in space, no one can hear you scream. Yeah, because there's no medium. It's a vacuum. There's nothing to be disturbed and propagate a wave in. Okay? If you're in the vacuum of space and you try to scream, no one will hear you because you cannot create, there's no medium to disturb with your vocal cords. Okay? So there would be no sound.
Okay, so there's, even if the ship's moving, you hear that?
Nope.
No?
That's totally a science fiction thing.
What if you're inside it?
Inside, there's air.
Yeah.
Right? So you can hear the vibration from the engines inside the ship because it would transfer through the walls and the walls would disturb the air and you would hear the vibrations and feel them. But if I'm in a spacesuit 100 meters from the ship, I won't hear anything. Okay? There's nothing there to carry the sound waves from the ship to me because space is a vacuum. I can see the ship. Light can travel through the vacuum of space, but not sound. Propagate needs to carry. Yeah. Okay. So a wave is a traveling disturbance. They require a medium in which to propagate. Okay. So in the figure below, if you're sitting in a boat, okay, and like in this little rowboat here, and a power boat goes by, it disturbs the water. Okay. As the power boat goes through, it pushes the water down. Water is elastic, so once the boat goes past, the water comes back up, and it oscillates up and down a little bit until the energy runs out, and then it quits. But if I'm over here, I feel the energy of that disturbance. It's carried by the water, okay, over to me, and my boat will oscillate up and down, okay, as a result. Okay? Does it take energy to lift my boat up and down? It does. Okay? That's the energy carried by the wave. Okay? So a wave is carrying energy from place to place. It's using the medium, in this case water, to carry that through. Okay? So the wave is a form of energy. The medium is where the energy is allowed to travel. Okay. The other thing we got to get our head around. A wave is not a bulk movement of water like a river. Okay? In a river, water goes from A to B. How does water move when a wave passes through? So the water that was under the boat, does it go this way and this way? No. The wave goes this way and this way. The water does this. Okay? What way did the boat push the water? Down. So the water moves back up when the boat passes by. All the water does is do this. Oscillates up and down, up and down. Okay? The disturbance travels away. That's the wave. The medium carries it. Okay? So the medium doesn't actually move from A to B. The wave moves from A to B. The medium oscillates. Okay? So let's say if we're watching one individual water molecule that's right here, okay, that water molecule has moved up and down already twice. Okay? And as this part of the wave comes in, it'll go up, and then as this part of the wave, it'll go down, okay, and it'll do this. Okay? That particular water molecule is just going to oscillate up and down, up and down, up and down. The wave is what's going to travel through it. Okay? Like, right now, you can hear me speaking. Is that because air is moving from me to you? I mean, it would be if and I'm not going to do this because it's COVID, but if I blew really hard, then yes, I'm pushing air towards you. But I'm just speaking right now. I'm not pushing air towards you. There's a disturbance traveling from my vocal cords through the air to you. Okay? The air is not moving to you. Okay? Everybody all right with that idea? Okay? Because if that was the case, if water moved along with the wave, all the water would end up on the shore. And there wouldn't be any in the middle of the ocean. Right? If you think about it, right? The reason we think that is because we've all stood on the shore of the ocean or seen waves or been at a lake or whatever and seen water come up, okay, like towards our feet or go past our feet. We've seen the water do this, move from A to B. But actually, that's not what it's doing. The water is moving up, and then the wave leaves the water. So it disturbs the water upwards and then runs out of water. So the wave actually leaves the water, travels into the air, and the water is no longer supported. So it falls down and splashes inwards. So what we see is the splash. Okay? If you were standing on the shore of a place where a tidal wave was coming, you shouldn't do that, but if you were, okay, you would actually see the ocean pull away before the wave came in. Okay? Because water is a polar molecule, so it bonds to itself, and as that water was displaced upwards, it would pull all the surrounding water up into the big tall wave, and then that wave would leave the water, travel into the air. You'd feel like a gust of wind as that wave leaves the water and travels into the air, and then the column of water it had disturbed would fall straight downwards and splash. In comes the wave. Okay? So it's actually not the wave we see inundate a coastal city. It's the splash. Okay? Does that sort of make sense? All right. So, got a couple of videos of that. Weird. Sorry guys, I put a new computer in here over Christmas and now it's, I forgot to sync this folder, so it's probably going to take a minute. Here we go. Okay, so, all right, get everybody's attention up here. Sorry that took so long. Okay, so what we've got here is just like the beach. Okay, the beach in Jamaica in this case. Okay, and we got waves coming in. That's my shadow. That's actually me because I'm a total geek standing there with my video camera videoing the waves on the beach. Because that's who I am. Right? All right, so what you're going to see here, okay, is, yeah, you're going to see the water moving kind of, it looks like it moves inwards, but really all that's happening is it gets displaced upwards and then falls and splashes in. And you can see that pattern if you're looking for it. Oh, I totally do.
All the waves sit right there. That's where they get big. Okay?
And I was explaining it to my son, Reed.
You hardly see them, and when they get that, they clear up and curl.
He's building a sandcastle. Okay, so now if you also watch this, you can actually see when the waves reflect backwards. Okay, because some waves travel back. And you can actually see in this, I got underneath the water to try and show how it was oscillating up and down. It's harder to see that. It's a underwater thing.
Is that Hawaii?
Jamaica. Okay, so really all we're seeing is, yeah, that gets displaced upwards and then it falls. And you can actually see it travel in both directions as it falls. Okay, so what we're seeing really is the splash. What happens is some of the momentum of the wave behind can carry some of that splash a little further forward. Okay, periodically what happens, sometimes you get that one wave that seems to be bigger than all the others. Okay, and that's the result of reflected waves going back out and interfering constructively and making the wave higher. And then it's even higher when it collapses, and then you get the bigger splash inwards about every 4 or 5 waves. Okay, There's other ones I'll show you, but I'll show them later. Oh, I know which one I want to show you. But I can't be recording when I show it. Okay, so there's two types of waves, guys. Those two types of waves have to do with the direction the wave travels and the direction the medium oscillates. Okay, so this first type of wave is what we call a transverse wave. And it's called transverse because the wave travels from left to right, but the medium oscillates up and down perpendicular to the direction the wave travels. Okay, or transverse is the other word for perpendicular. So this is a transverse wave because I disturb the medium, in this case the slinky, up and down, and the wave travels away from the point of disturbance. Okay, now, so here's another example of that thing we were talking about where a wave doesn't take the medium with it. Okay, a wave travels through the medium. If I oscillate a spring up and down, the spring doesn't run away from me. Okay, the waves run away from me, but they don't take the spring with them. Okay, all the medium does is oscillate up and down because that's what I'm making it do. It's the waves that travel away, and the energy that I put into disturbing the medium is carried by the waves through the medium, and it is eventually lost to friction and stuff like that. Okay, so that's a transverse wave. Okay, so a wave is a traveling disturbance, and then a transverse wave, okay, the wave is traveling from left to right, but the medium oscillates up and down. Okay, so a transverse wave is one in which the disturbance is perpendicular to the direction of travel of the wave. Okay, now same terminology applies that we talked about before. Amplitude is still the maximum distance that the medium will move from its equilibrium position. Okay, before Christmas, we were talking about masses on a spring, okay, and how their amplitude was the maximum distance that the spring would move or the mass would move from its equilibrium position. That is still true for waves. Okay, and it's the amplitude of a wave that determines the wave's energy. Okay, speed of a wave doesn't really play a part. Okay? And I know that seems counterintuitive because all the way along we've been saying that speed affects the kinetic energy of an object, and it does. Remember, a wave is not matter. Okay? Here's the other part of it. All sound travels at the same speed. So, if I whisper, okay, that sound has the same speed as yelling at you. Okay, but which one has more energy? Me yelling, right? Okay, the amplitude of me yelling is way bigger than the amplitude of me whispering. Okay, but they travel at exactly the same speed. The speed of a wave is actually determined by the medium in which it travels. So speed has nothing to do with a wave's energy. It's determined by the medium itself. Okay? So, for example, if the air temperature outside, it's nice today, it's about 6 degrees, so the speed of sound outside the window is about 336 meters per second, but in here, it's 343. Temperature, yeah, okay, there's a temperature difference, that's a property of the medium. Warmer air, faster wave. Cooler air, slower wave. Okay. All right. So, got a couple other videos here I'm going to show you about big waves, tsunamis, because people always ask about tsunamis and stuff like that. Okay, they're a little bit older now, so they're a bit dated, but they're still scientifically true. What we're looking at in that video is like earthquake-created or propagated waves. Okay, so they're the result of something lifting up the ocean from beneath and causing basically a small series of waves, or one really big one. Okay? But most of the waves that we see on the ocean are the result of what? Wind, actually. Okay? Most of the waves that we see, even ones that are that people surf, are wind-driven waves. The mechanism that creates those is a little bit different. Okay? Because now you've got a disturbance that's kind of across the top of the water. Okay? As opposed to lifting from below. So what actually ends up happening is you got wind that's pushing on the surface of the ocean, not directly across, but a little bit into it, pushing it down, but also creating a bit of a cyclical pattern. Okay, and so that's where you see the rolling of the waves. Okay, so have you ever seen somebody surf? It's really cool when you see the wave curl around them and they're kind of surfing out of the kind of gap in the middle. Okay, those are wind-driven waves. They work a little bit differently, but it's still an oscillation. Okay, it's more of a circular oscillation, but it's still an oscillation. Okay, so I got another video on that that's like surfer science dudes. Okay. Where is it here? So obviously one of the big concerns with a wave that's doing this, okay, that's having like a cyclical kind of a rotation and oscillation, is that if you get caught in it, you get tumbled. Okay, and that's what gets surfers. Okay, if they fall off their board, you kind of have to just let things happen, because if you fight it, you'll tire out and you might be swimming in the wrong direction. You don't have a sense of up and down when you're being rolled underwater. Okay, the weight of the water kind of hides the effect and the pull of gravity, and you don't know which way is up. And what a lot of surfers will tell you is they're swimming really hard, thinking they're headed for the surface, and they come up with a handful of sand. Okay, so they've wasted all this energy swimming in the wrong direction because they had no idea which way they were going because of the rolling of the water. You basically have to just let your buoyancy carry you to the surface. Okay, and hope that your board is also doing the same thing. That's why they're usually tied to it. All right, so properties of the waves, we've got amplitude, we've got wavelength. Wavelength is represented by this symbol here, which is lambda. It is the Greek letter L. Okay, we can't use L because L already stands for length. Wavelength is represented by lambda, the Greek letter L. All you have to do for lambda is draw a long line leaning on a short line. Okay, that's lambda. Okay, and it represents wavelength, and it's in meters most of the time. Could be centimeters, but most of the time it's going to be meters. Okay? So the wavelength is the distance between any two successive points on a wave. So from one crest, that's the top or high part of a wave, to the next crest. Okay? Any two successive points. So crest to crest, trough to trough is one wavelength. Okay? Any two equal successive points are always going to be one wavelength apart. Does that make sense? All right, so that's for transverse waves. Okay? Now, terminology is still true for longitudinal waves, but longitudinal waves don't go up and down. Longitudinal waves go back and forth. Okay? All right, so a longitudinal wave oscillates parallel to the direction the wave is going. So the wave is going from left to right, and the wave is oscillating back and forth instead of up and down. So now it's longitudinal or parallel as opposed to transverse. Okay? So a longitudinal wave doesn't have crests and troughs. It's got compressions and rarefactions. So a compression is where you're squeezing it together, and a rarefaction is where you're pulling it apart. Okay, if we're talking about a spring. If we're talking about a sound wave, okay, sound waves are longitudinal waves, okay, and they result from compressing air and rarefying air, compressing air and rarefying air. Okay, so if you've ever watched a subwoofer moving, that's what it's doing. Okay, when it moves forwards, it's compressing the air. When it moves backwards, it's rarefying air and it's creating a sound wave. Okay, subwoofers move slow enough that we can actually see that happen.
Is it? It's like a chair like that then? Like a compressed chair that moves up and down?
Well, it's compression, but it's hydraulics. It's not creating waves, but it is using pressure. Yeah, not quite the same thing, but it is using pressure, yes. Okay, so compressions and rarefactions are how we make longitudinal waves, and that's what our eardrums are set up to hear. Okay, so when sound waves strike our eardrum, a compression pushes the eardrum inwards towards the center of our head, and then a rarefaction essentially sucks it outwards a little bit, okay, away from the center of our head, and that oscillation tells our brains we're hearing this sound. Okay? How quickly it oscillates back and forth is the pitch or frequency of the sound. Okay? How far it moves is the amplitude or volume of the sound. Okay? That's why frequency is not what ruptures your eardrum. Okay? It's volume that can rupture your eardrum. Okay? It's about how far your eardrum has to move, not about how fast. Okay? We can hear sounds, okay, between 20 hertz and 20,000 hertz in general. Okay? That'd be the average person. Some people can hear higher and lower sounds than that. Okay? But in general, that's the range of human hearing. If I hear a sound, if a sound is happening that's hitting my eardrums that's 40,000 hertz, like let's say a dog whistle, okay, which dogs can hear but we can't, that's never going to hurt my ear. Okay? My eardrum cannot move fast enough to detect it. So my brain doesn't hear it, my ear doesn't hear it, my brain doesn't hear it, I don't hear it. Okay? Similarly, you could have really low frequency sounds. Okay? You can get sounds that are so low you don't hear them, you feel them instead. Okay? That would be really, really low sound. So a subwoofer typically is going to be amplifying sounds between 30 to like 100 hertz. Usually it's around 60 hertz is kind of where you set your subwoofer to really go. Okay, that would be the rumbling bass, okay, that you can create with a sub. All right, so the bigger the wave, the louder the wave, the greater the amplitude of the sound. So the further your eardrum will go. Now, what is your eardrum attached to? Little bones. Okay? In your middle ear, remember, and you probably remember this now from junior high, you got the hammer, the anvil, and the stirrup. Okay? The three bones that it's attached to, okay, that are attached to your eardrum. Okay? So they're the ones that are responsible for transferring the vibration of your eardrum to the auditory nerve, which then can be interpreted by your brain. Hearing loss occurs because of damage to usually those little bones. Not so much the eardrum. If your eardrum perforates, that's it. Okay? You're never going to hear out of that ear properly ever again. But we can cause small amounts of damage to the little bones in the middle ear. How many of you have ever had your ears ring? Right? Went to a concert, or you're sitting in, like guy's car, you know that guy? Okay? The roving rave guy that drives around. Okay? If you're, then after a while, your ears ring. Okay? If your ears are ringing, you've essentially done what happens if you sprain your ankle. But you've done it to the little tiny bones in your ear. Okay? Anywhere where two bones meet is a joint. And joints are connected by ligaments and tendons. If I sprain my ankle, I overstretch the tendons and ligaments in my ankle. And it swells and it hurts. And it's weak after that for a little while. And then it heals up. And scar tissue forms around the ligaments and tendons. Same thing happens in your ear. Every time your ear rings, you've essentially sprained the little joints inside the ear. The ringing is a result of the swelling. So now when you move your head around, the little bones move because they're inflamed and there's extra fluid there. Okay? They move around, they create this ringing sound that's not actually there. But your brain hears it because these bones are hurting, essentially. Okay? And so every time you do that, a little bit of scar tissue forms between the bones, and they become less flexible. Okay? So what happens is your range of hearing starts to narrow. Okay? That's hearing loss. That's how hearing loss happens. So every time you make your ears ring a little bit, you've done just a little bit of damage permanent to your hearing. Okay? It's small, but it adds up over time. It's cumulative. Okay? So think about that the next time you got your beats on, okay? And you're pounding away, and you take them off, and you get that sensation of like a wave or pressure on your ears when you take them off. They've been too loud. Okay? You got to go easy on your ears. Okay? Your generation is probably going to have more hearing problems than any previous generation because you guys have had access to mobile music and electronics more than any other. Okay? When I was a kid, we had like the big orange foam Sony Walkman that was a brick that had a tape in it. Took like 6 AA batteries, lasted about 45 minutes. Okay? And then that was it. Okay? Whereas you guys can go around all day on a charge with these tiny little wireless phones that stick right in your ear. Okay? The ones that stick right in your ear, they don't allow pressure to escape. Okay? They can do even more damage. So you have to be really careful about that. You're going to want to hear your children laugh. I know you're all saying you're not going to have children, and some of you might not, but it's a nice sound to hear your children laugh. You don't want to be deaf. Okay? Yeah. So keep that in mind. Keep the volume to a reasonable level.
What happens when your ear pops because of a change in pressure?
Okay, your ear pops because it changes in pressure, not hurting your ear at all. It's just balance, equalizing the pressure. So if you've descended really quickly or ascended really quickly, there's a pressure difference on either side of the eardrum, and it just takes a few times for you to clear the eustachian tube, which runs from the middle ear to your throat. So you swallow a couple of times, usually it'll pop, chew some gum, and the movement will usually allow the pressure to equalize. If the pressure doesn't equalize, it becomes very painful because it starts to stretch the eardrum. Does that sort of make sense?
Yeah.
Yeah.
Does that mean when your ear just rings like randomly, like even if you're not listening to loud music?
And it can happen because of, again, like your ear popping. Sometimes it'll ring before it pops, it's just a pressure thing. But if it's ringing because you've exposed it to really loud sounds, you have done damage. Sometimes your ear will just ring. Usually it's just a result of a little bit of inflammation. Sometimes it can be an infection. If you get an ear infection, right, the same thing can happen.
What would be the issue like if you burst your eardrum?
Okay, if you perforate your eardrum, then it will, like, it's basically just a thin flap of skin. So it's very difficult for that to heal and have any flexibility after. So it'll heal, but it'll be all scar tissue. And usually what happens when it tears is the bone disconnects from it, stuff like that, and it just never is the same. You're usually legally deaf in that ear if you perforate your eardrum. And you can get some hearing back, but it's never like it was. Yeah?
So if you're punched in the temple, why would you do okay?
Well, anytime you get punched in the head or hit in the head by anything, it rocks everything inside your head. That's why you get a concussion. But it's the same thing. A violent movement of the head is going to cause the stuff in the middle ear to move as well. Okay? And any abrupt movement like that is going to cause a ringing. Right? Usually you see stars, like it affects the optic nerve just as much as it affects the auditory nerve. Right? Anything that affects your brain affects anything that's attached to it. Okay, so does everyone understand the longitudinal wave part? Okay, compressions and rarefactions. Okay, so if we make in a slinky, we can make compressions and rarefactions. We just oscillate it back and forth, okay, and we can create these waves. Okay, but again, that is we're just watching a single ring in the slinky. All that ring is doing is moving ahead and moving back and back to equilibrium again. So the disturbance disturbs it to the right, then back to the left, and then back to equilibrium, and the disturbance is gone. Okay, so we can see that traveling away. It's the part highlighted here by that kind of greenish bracket here. Right? That compression is moving away. All right, so I think I have a couple of videos. Okay. So good analogy here has to do with like a train moving by. Okay, so the speed of a wave is, like we said, determined by the medium. So whatever it's traveling in determines how fast it can go. A wave is going to travel faster in water than it can in maple syrup. Okay, because they have different fluid properties, they're different media, so the wave travels differently in each one. Okay, so if it were comparing it to a train, the number of cars that go by every second would be the frequency. How long it takes one car to go by would be the period. Okay, things like that. Okay. So waves are just an example of simple harmonic motion. If we're looking at a mass on a spring as it oscillates up and down, okay, if I was to put like a pen on the bottom of the ball and then pull a piece of paper under the ball as it oscillated up and down, I'd get a wave on the paper. Actually, I have a video of that. Okay. Now, something else that I want to cover here real quick has to do with the thing we're going to talk about tomorrow, which is the universal wave equation. Okay, so that formula is on your formula sheet. That is the universal wave equation. The speed of a wave is equal to the frequency of the wave times the wavelength. Okay? It can also be written like this. Wavelength divided by period. Okay, so if we take the wavelength and we divide it by the period of the wave, we'll also get speed. And that's because this is in meters and this is in seconds, okay? This is per second, right? It's hertz, okay, times meters, meters per second. So we get meters per second no matter which way we use the formula. This is the way it's written on your formula sheet. Okay, so we were talking about how when waves approach the shore, they get taller and they get shorter, okay? So this property of a wave can change. This property of a wave can change. This property of a wave never changes, okay? Nothing can change the frequency of a wave once it's produced. Its frequency is controlled by the source, okay? So what that means is, if I have a red light, nothing is going to make that light look green, okay? Because the color you see is based on the frequency of the light that's being emitted, okay? Nothing's going to make that red light look anything other than red, okay? Doesn't matter whether I make it go faster or slower or whatever, okay? It's always going to look red. And the reason for that is, if the speed changes, what happens to the wavelength? It changes too. Okay? So we said we had long waves out in the ocean. Okay? Well, those long waves are moving very fast. So lambda and v are both big. As they get closer to shore, they slow down. And what happens to the wavelength? It shrinks. So when one of these changes, the other changes as well, and changes by the same amount, which keeps frequency always being the same. Frequency is v over lambda, and these two things change together always. Okay? Everybody with me there? Okay, so the frequency of a wave can never change. Another place where we can kind of see this is probably an experience you've all had. So just out here, by the traffic lights, just ahead of them, the speed limit changes from 100 to 60. Okay, so right there is the line. Okay, this is 100 kilometers per hour. Okay, and this is 60 kilometers per hour. I have an observer here, and I have an observer here. Okay, so out here at 100 kilometers per hour, there are 3 cars. And they're traveling all at 100 kilometers per hour. The observer sees 3 cars go by every second. Okay? This observer here sees 3 cars go by every second, 3 hertz. So does this one. Same 3 cars pass that observer, but now they're going 60 kilometers an hour. How does this person observe all 3 cars going by in 1 second if they're going slow?
Because they're all going the same speed.
Well, they're all going the same speed, but they're going slower. How does he see just as many go by him in a second if they're going slower? Exactly, they're closer together. Okay, this one reaches the 60 kilometer an hour boundary first and slows down. This one doesn't. Okay, it doesn't slow down until it gets to the boundary, which means it catches up. Right, the distance between them is going to shorten. Okay, you guys have all taken, driver's ed, or at least passed your driving course probably. Okay, got your license. Following distance is affected, right? You don't follow as close if you're going really fast. Remember that. You're not supposed to follow as close when you're going fast. Don't tailgate. Okay? So when it's 60 kilometers an hour, those same 3 cars are going slower, but they're closer together because these cars catch up when the first car slows down. The back car catches up to the second car because it slows down before the back car does. So I still see 3 hertz in both places. The frequency doesn't change because the speed and the wavelength do. Okay? If they slow down, they get closer together. Okay? Same for cars, same for waves, always going to be true. Okay? Frequency never changes. I don't know if anybody's written that down, but I've said it like 10 times in the last 5 minutes. It's super important. The frequency of a wave never changes. It's the one property of a wave that cannot change. Okay? And it doesn't change because the other properties of the wave do. Okay. Will this be a very hard formula to use? It will not. Okay? It's quite simple. The tricks for universal wave equation problems are the context of the questions. You have to be very careful about the wording of the questions. So I'm going to give you an example here. A person is sitting in a boat and they observe 5 crests passing them. How many waves went by? That's our gut reaction. Okay, there's 5 crests. They started counting here. One wave is one complete cycle. 1, 2, 3, 4. Okay, 5 crests, 4 waves. Okay, now the question could have also said a person is sitting in a boat and oscillates up and down 5 times. Now how many waves went by? 5. Okay, if it says they oscillated up and down 5 times, that's 5 waves. If it says 5 crests, that's only 4 cycles. They started on the first crest, and the wave only cycled 4 times. Okay, so it's context that can be a little bit confusing.
So if we get a question like that, are we to assume that the wave starts at like the midpoint between looking down and up?
Yeah, if they're saying you're counting crests or troughs, then they're saying this is crest 0. And now there's 5 more. Yeah, does that make sense? Okay. All right. What about an echo? So if I, like, let's say, shout at a mountainside, okay? When I hear the echo, how far has my sound traveled? There and back again. So echo questions trick people because they usually say, you know, you're standing, here's your mountain, and you were standing here, and it says something like, you hear the echo 5 seconds later, and you shouted with a frequency of, let's say, 300 hertz, and the wavelength of your waves was, I don't know, 1 meter, let's say, or 0.9 meters. Okay? And you hear the echo 5 seconds later. Okay? How far away is the cliff? That's how an echo question would work. So, right now, if I want to calculate how far away the cliff is, I'm looking for distance. I have a time, a frequency, and a wavelength. What do I not have that I need to get d? Velocity. Now, will this formula calculate velocity? It will. Okay. Sorry, I just realized I made a mistake with the wavelength if I want this to work right. I want it to be 1.1, not 0.9. Okay, so I want to calculate the speed, because if I know the speed, then I'll be able to calculate the distance. So speed is going to equal 300 times 1.1, which will be 330 meters per second, which is the speed of sound at like -1 degree Celsius or something. Okay? All right, it took 5 seconds for me to hear the echo. How far away is the cliff?
66 meters in one direction.
Right, I only want this distance. It took 5 seconds for the sound to go here and back. How long did it take the sound to get there? 2.5, half of this number. Okay, we have to remember that echoes travel there and back. That's the trick with echoes. Okay, so I would say D equals V times T, 330 times 2.5 seconds. Okay, not 5 seconds. 5 seconds is how long this give me how far it is to the cliff and back again. Okay? So little things like that. The math in this unit is really easy. Okay, like this is basically V equals D over T. Okay, but applied to waves. Right, and that's what we're going to look at tomorrow. All right, I need you guys to clear up your desks because I gotta wipe them down. So everybody put their mask back on. Okay, sanitize your hands, all that kind of good stuff.
If someone really needs to God, you're stuck in the box. Good Lord. That's very close to me.
That's like outside the clinic lips,
Honestly,
Fuck did you collapse today?
I always stare at
Yeah, I believe that.
What? Not you.
So, do you have like
I'm sure the last.
Back, reverse, into my